Hello students, today we are going to understand the general theory of one-dimensional harmonic oscillator. We are going to solve the general equation of motion for a one-dimensional harmonic oscillator using the concept of Lagrangian equation. So let's consider a stable system, or I can say consider a system which is in a stable equilibrium, and let the system possess 1 degree of freedom. So I have 1 degree of freedom, and so that means I can specify the system using one generalized coordinate. So that generalized coordinate be q. Now for a small displacement from the equilibrium, so let the equilibrium position be q0. For a small displacement from the equilibrium, say to the position q, then the potential energy of the system at the position q, which is slightly away from the equilibrium, or I can say that the system has been displaced from the equilibrium to the position q, then the expression for the potential energy can be written in terms of Taylor series expansion. Any system about an equilibrium point, about a position, can be written, that function can be written in terms of Taylor series. You have learned that. So I can say the potential energy function at q can be written in terms of Taylor series as vq0 plus first order differential dou v by dou q at the equilibrium, okay, and q minus q0. Next coming the second order term, that is 1 by 2 into dou square v by dou q square at the equilibrium into q minus q0 whole square, then all the higher order terms. Okay, so now you look at this equation at equilibrium. So what happens at equilibrium? So I can say that at equilibrium, this is a general expression written for about the equilibrium point, that is at q. Now at equilibrium, you know that this term, we have learned that the potential energy is maxima or minima for a stable equilibrium, right? So the potential energy dou v by dou q at the equilibrium position will be equal to 0. That you have understood. So that means this term will vanish, and all the higher order terms, if we neglect, then I can, the second order, this term we can take in, and the other higher order terms we are going to neglect. So then I can write the expression, which is the Taylor series, will now change to VQ equal to, then this term VQ0 we can take, we are taking the potential energy at the equilibrium. So it means that potential energy at the equilibrium is VQ0, and that can be considered to be 0, since it is the initial potential energy, and you know that the potential energy is very lowest there. So just reminding once again, since the first term in this series is at the equilibrium, we take this VQ0 at 0, and now since the potential energy is minimum, then dou v by dou q also becomes 0 at equilibrium. Then I can rewrite this Taylor series expansion as half into dou square v by dou q square 0 into q minus q0 the whole square, right? Now let me put this dou square v by dou q square as equal to k. Let me take this as equal to k. Then this expression becomes Vq is equal to half into k q square. Okay, now obviously this term, this dou square v by dou q square, since it is a concave, we know that it is stable equilibrium, then the curve is a concave thing, concave curve. Then I can say that this dou square v by dou x square is obviously a positive parameter at the position of stable equilibrium. That is, if the curve was like this and if the system is in the unstable equilibrium, at this point I can say the dou square v by dou q square, where the curve is a convex type, then the dou square v by dou x square becomes negative. So here it is k is a positive parameter. So this becomes the general expression of a potential energy, which we normally write as half kx square or half k. Instead of x, we have written here q as the generalized coordinate. So here the potential energy function finally turns out to be half kx q square, starting from writing the Taylor series expansion. Next, now the generalized, you know that the position of the system here, that is position depends on only the position, the generalized coordinate, and does not depend upon the time explicitly. So it doesn't depend upon the t. Okay, then in that case I can write the x dot is equal to dou x by dou q into basically dq by dt, right? This you have learnt in the preliminary sections, that is x dot can be written as dou x by dou q, because x is a function of generalized q, and here it is not a function of t. If it is a function of q, generalized coordinate, then the position. Okay, then I can write this x dot, that is velocity or the first order derivative, as dou x. Since it's a function of q, I can write dou x by dou q into dq by dt. So this is actually dou x by dou q into q dot. So then I can write the kinetic energy of the system, which we have been talking about. We have already written the potential energy. Then the kinetic energy can be written as half m x dot square. You know that. So that is half into m into x dot square. We can substitute this. So I can write dou x by dou q the whole square into q dot square. Okay. Then I am writing this term, that is I consider m into dou x by dou q the whole square as m function of q. Okay, so then I can write it as half m, a general function, where m is a mq is a general function of q. Then I can write this as half m into m function of q into q dot square. So got the kinetic energy general expression. So first, in the previous section, previous discussion, we got the potential energy, and now we got the equation for the kinetic energy. Okay, now this coefficient mq can also be written in or expanded in terms of Taylor series. This mq, which is not exactly the mass, so m, we understood that it is also a function of q. So earlier v was a potential energy was a function of q, then we expanded the potential energy about the equilibrium position in terms of Taylor series. Similarly, in terms of Taylor series, using Taylor series, I am going to write this mq about the equilibrium point. Then I can write it as m q0 plus dou m by dou q at the equilibrium into q minus q0. Okay, now putting this equilibrium position, let me take the equilibrium coordinate q0 as equal to 0. So putting this the equilibrium position q0 as 0, then I can write it as m of q is equal to m0 plus dou m by dou q at 0 into q plus the higher order terms. I'm not going here for the higher order terms, because if I put this here for the expression for kinetic energy, this becomes half mq, this becomes this, then it is q dot square, right? So it is already quadratic. Q dot square is coming in already in this equation. So if I multiply this, the whole thing for mq, if I substitute this, and then q, since there is a q dot square here, already this is quadratic, then becomes, we can see that all the very higher order terms will come if I repeat the like dou square m by dou x square term if I take in, then the equation becomes more so much higher or higher in order. So here I'm only restricting this mq to the first order derivative term alone. So now we are going to write the Lagrangian of this one-dimensional harmonic oscillator. Okay, as we got the t and the v. Okay, now writing the Lagrangian, then I can write it as L is equal to t minus v. So t is half m mq, and mq is m0 plus dou m by dou q, like this, right? So I can I forgot one thing here also. This thing, if I put m0, then I can, instead of mq, I can write m0 plus dou m by dou q at 0 into q, then q dot square. So even if I put this term even here, then q dot square into q, it becomes cubic, right? So I am not taking, because of that, since restricting this equation to quadratic, to the second order term, what I am going to do is I am not going to take this here. Okay, so that higher order term is also being neglected. So I substitute, instead of mq, m0 alone. I hope you understood, because there is already a q dot square here in this expression. So we retain only this first expression here. First this mq is retained as m0 alone. So now I can write this expression as half, and instead of mq I can write m0, then q dot square minus half into k q square. Okay, now the equation of motion, Lagrange's equation of motion is d by dt of dou L by dou q dot minus dou L by dou q is equal to 0. Then d by dt of substituting for Lagrangian, that is dou by dou q dot of L is half m0 q dot square minus half k q square minus dou L is dou by dou q of half k q square equal to 0. Now d by dt of, see, derivative of derivative of this term with respect to q dot. There is no q dot here in the second term, so this derivative of this term with respect to q dot becomes 0. So this other expression becomes half m0 into taking the derivative of q dot square with respect to q. This becomes 2 into q dot, right? And this becomes minus, taking the half derivative, I will get half k to q. This is equal to 0. So this equation can become 2 and 2 will become cancelled. So this becomes m0 q double dot, right? Then sorry, here also if I take dou q by dou q of L, I had to substitute the whole thing, and since this is q dot square here, if I take the derivative of q with respect to q dot with respect to q, that becomes 0. So this term had, like, this terms becomes, it is actually there here, this term is there, minus of this half m 0 q dot square, then minus this half kq square. Okay, so that was there. This term turn out to be 0 when we take the derivative. Then there is a negative here. Okay, so that negative with a negative here, this becomes positive. Okay, so this becomes half kq, that is plus half, this will get cancelled, that is kq will be equal to 0. So this becomes q double dot, if I so that if I take this m, if I bring or if I divide the whole equation by m, then I will get this expression as q double dot plus k by m, right? And this k by m into omega, so q is equal to 0. As you all are familiar with this term, or almost this expression, you may be familiar, then I can write this term k by m at 0 is mostly considered as omega square. So then I can write this expression as q double dot plus omega square q. Instead of k by m, I substitute omega square, and that is equal to 0. Now this is the expression of motion which we got for the one-dimensional harmonic oscillator. Then considering the small oscillations, for such an equation, let's assume, we can assume the or we further solving this equation, normally we do is it in this way. We assume a particular solution for that, and then find out the, for that particular assumption, how do we match for. So let me consider this solution for this expression as, solution should be for q, right? So q is equal to a into e raised to alpha t. The only thing is I have to find what a and alpha is. Now substituting, let me write what is the equation number here. Three, and here the equation number 4. Let me put this solution for this equation. So let me put that in equation 4. Then if I put that in equation 4, q double dot is first q dot is a alpha into e raised to alpha t, right? Again taking the derivative, so this becomes second derivative, order derivative, it becomes a alpha square into e raised to alpha t, right? Second order derivative, and we apply here q double dot, this becomes like this. Then omega square into q is a e raised to alpha t is equal to 0. A into e raised to alpha t is there in the both the expression, so e raised to alpha t, if I take this expression, becomes alpha square plus omega square equal to 0. This is the solution I have written, a into a e raised to alpha t, and that solution can never be 0. So the only option is alpha square plus omega square has to be equal to 0, which implies that alpha is equal to minus omega, so alpha square is minus omega square, or alpha is equal to square root of minus omega square, and that is equal to square root of minus 1 is I omega, but then since it is square root, it can be plus or minus I omega is actually alpha. So therefore the general expression for q can be written as q is equal to a for e raised to I omega t is also there. Okay, one solution for alpha, that is a e raised to instead of alpha I got plus or minus I omega. So there will be two solutions, a e raised to plus I omega t and a e raised to minus I omega t. So that coefficients may change in both the case. So I can write it as a1 e raised to I omega t, or q can be equal to a2 e raised to minus I omega t. So these are the two solutions. Hence the general solution can be written as q is equal to a1 e raised to I omega t plus a2 e raised to minus I omega t. Okay. Now see, this q is basically the position, generalized coordinate. So that means this q should be a real number. If the q has to be a real number, you know that e raised to I omega t basically is a complex number. When we write in terms of trigonometric sine and cosine functions, this becomes basically a complex number. So then so for the q to be a real, then what can we say? If q has to be real, this complex number has to be multiplied by another complex number, then only this q can be a real number. So that I can say that this a1 and a2 are complex conjugates. So then I can write a1 as equal to, okay, so here this a1, you can say that e raised to I omega t is actually cos omega t plus I sin omega t. Okay, so if I multiply, if q has to turn out to be a real positive quantity, a real number, then a1 must be again a complex number. So that complex number, when I multiply by this one, finally q turns out to be a real number. But then that a1 should be the complex conjugate of this one. So that there should be a negative sign for this a, right? In like if I as I write e raised to omega t, if I consider a1 as some complex number, then that should be the conjugate, something like it should be a conjugate of this. So then I can write this a1. So I consider this a1 as half into c minus id. You will understand why this half comes in. That is actually for the simplification easiness. And then I am supposing that a as equal to half into c minus id, and as the complex conjugate of this number, and then a2 as half into c plus id. C plus id is taken because here it is I raised to minus I omega t, that is cos omega t minus I sin omega t. So that's the opposite sign in the middle I have taken. So now what you have to do is, you have to put it in this q. You know that q is equal to a1 half into c minus id, okay, e raised to I omega t, and e raised to I omega t, okay, let me put it as e raised to I omega t plus a2 is half into c plus id into e raised to minus I omega t. Now what you have to do is, you have to simplify this equation. It can be easily done. You open the brackets and then you can easily simplify this expression, and finally, and that is your assignment, you have to do that, and finally you will get this q as equal to c cos omega t plus d sin omega t. Okay, so this has to be done by you, and then finally we get this q as this much. Now if I write the c and d as a cos 5 and d as say a sin phi minus a sin phi, I have to substitute. Instead of c I put a cos phi, and instead of d I put a sin phi. Okay, then this expression will turn out to be Q is equal to that. Also you have to do, and then you have to find out. If I put C instead of C, I put A cos phi, then it becomes a relation like a, if I take A outside, it is cos A cos B minus cos A sin B, cos A, cos A cos B minus sin A sin B, and this becomes A into cos omega t plus phi. So this is the general expression for this one-dimensional harmonic oscillator, which you are very familiar with. And this constant A, you know what it is, right? It is the amplitude. And what is omega? Omega is the frequency of the oscillation, t is the time, and phi is the initial phase of the oscillator. So this is all about the deriving the general expression for the one-dimensional harmonic oscillator. So with this basic understanding, now we have to move on analyzing the coupled oscillators. Thank you.